Then we also learned about what are the challenges that we face while doing observational astronomy. Then the next section was about history and basics of observational astronomy, and it included day-to-day observations that our ancestors did and that we also can do, and also some anomalies in the sky, for example retrograde motion, which is an apparent backward motion of planets, and other things such as smudges in the sky or some events that occur in the sky. And then based on these we made some inferences and some models, for example the model of eclipse and the model of our system of sun, moon and earth. So based on very simple observations we made some models. Then we moved on to telescopic observations, in which we learned how Galileo, Nicholas Copernicus and Aryabhatta and these people taught us what our solar system actually looked like. Then we learned about some catalogs and then some other observations of Galileo, such as phases of Venus and Jupiter's moons. And we came to the heliocentric model. And at last, we learned some techniques and some methods of amateur astronomy, of about how to orient yourself when you're looking for a star or a stellar object, and what catalogs you should be aware of, and how to measure angles using your own hands and without any equipments. And then at the last we talked about some magnitudes. But since we ended with magnitudes, let's today also start by looking a little more into the magnitudes. So last time we read about Hipparchus of Rhodes, and he was the guy who basically gave us the method to measure brightness, and he did it like a ranking system in which he went from bottom to top, and he gave the number 6 to the dimmest object in the sky and 1 to the brightest. In his catalog, however, it was only about stars and not about like moon or sun or planets. So his catalog was a little bit incomplete, and he told us basically about the magnitude of brightness or magnitude of an object. So in layman's term, magnitude is simply how bright a star is, but when we do physics we quantify stuff, and to quantify it, one object of magnitude 1.
Thank you, sir.
Yes. Is there a query? Okay. So an object of magnitude 1 is basically 100 times brighter than an object of magnitude 6. And for each increment, then we calculate that this would be the increment for each rank from 6 to 5 and 5 to 4 and etc. So basically now this has been laid out in form of a formula. So let's say if something bright is shining and my eyes are capturing it, so basically I'm observing the photons or electromagnetic radiation that is coming through my eyes, just this area and only this area, and that thing for some radiation or some particles passing through a specific area, we call that as flux in general. This is not a very hard fast definition of flux, but you can understand in this way. And in this formula basically we are looking at if the flux is 100 times the that of other object. Flux from one star, let's say, is 100 times that from other star, then it's basically how much of a change in ranking of magnitude will you get. So for example, here is M2 and M1, and if we say 100 times the flux there is, it's 100 times brighter, then there is a change of 5 ranks. So from rank 6 we move up to rank 5. This is basically kind of a mathematical statement of this exact statement. बेसिकली हमने लास्ट टाइम हिपार्कस ऑफ रोड्स के बारे में पढ़ा था. उन्होंने कैसे हमें मैग्नीट्यूड डिफाइन करने का एक तरीका बताया, एक इनफॉर्मल तरीका था वो. बट धीरे धीरे क्योंकि हम फिजिक्स पढ़ रहे हैं, तो फिजिक्स में बहुत जरूरी होता है कि हम किसी भी चीज को अच्छे से क्वांटिफाई कर पाए, उसका एक्चुअल माप निकाल पाए. तो उसमें हमने ये फॉर्मूला देखा है जिसमें कि बेसिकली ये स्टेटमेंट जिसमें बताया गया है कि रैंक 6 से लेके रैंक 1 तक 100 टाइम्स ब्राइटनेस होती है। उसी का एक तरीके से मैथमेटिकल वर्जन है ये, जिसमें हम देखते हैं कि अगर 100 टाइम्स किसी ऑब्जेक्ट का फ्लक्स है या फिर ब्राइटनेस है, तो उसके मैग्नीट्यूड में कितना चेंज होगा, होगा रैंक 5 का चेंज। सो इट्स द सेम एज दिस स्टेटमेंट. Now about luminosity and absolute magnitude. So we kind of understand what flux is, right? Flux is, in other words, kind of like brightness of an object. But then there is luminosity or intrinsic brightness. So what is intrinsic brightness? It's energy emitted from source in all directions per unit time. So that's basically flux, which is brightness, multiplied by the all directions. So that would be 4 pi d square per unit time. So now in order to calculate flux, we divide the luminosity by that area quantity. And then there is also there is already this formula, and then we have also absolute magnitude, because apparent magnitude might be misleading sometimes, since object might be closer to us, that's why it's brighter, and it might be simply bigger, that's why it's brighter. So we don't exactly know if it's actually brighter or it's just close to us. So in order to make sure we have correct value of magnitude, we have defined a term as absolute magnitude, and its measure of luminosity of a celestial object at 10 parsecs. If you were standing at 10 parsecs from an celestial object, the apparent brightness of that object at that distance specifically would be absolute brightness, sorry, absolute magnitude. So for that, we basically observe flux at 10 parsec, and we get, we observe luminosity at 10 parsec, and then we get the flux at 10 parsec. And after observing flux at 10 parsec, we can easily get the actual absolute magnitude. Now moving on to the next section of this webinar, that is advanced astronomy. So in advanced astronomy, we start learning about how our what our observations has led us to conclude, and what we have learned so far. And then we develop on those things, and we try to make some equipments. We try to better our understanding by applying logic to it. And one of those things that we do is understand and study lenses and mirrors. So obviously, a lot of you, I'm assuming all of you, would have seen a plane mirror and how it works. But there are other shapes to mirrors and lenses, and we'll study about that. So in first section, you can see a plane mirror. In this plane mirror, there are some rules that light has to follow, or basically we have made those rules based on what light does in real life. And the rule is basically the angle of incidence is equal to angle of reflection. You might have studied in your physics class. So we make a 90-degree line, imaginary line, and light incident on it makes an angle, and light reflecting makes an angle, and those angles are same. The same thing applies in spherical mirror, but in a certain different way, because it's a spherical mirror and it cannot have a single normal line, since since it is curved basically. So we assume that a curved or spherical mirror is basically similar to an array of multiple plane mirrors, very small plane mirrors, an array of that. So after doing that, we, based on where the uh, incident ray is hitting it, we, based on that, kind of calculate where the reflected ray will be, drawing a normal there. But we also have developed some rules about it. So one of the rules is like, if a ray is coming parallel, then all of the light would be reflected and intersect at a point called focus. So that is one of the rules, and that is how we study and understand lenses and develop equipments using it. And similar to this spherical mirror, in convex lens, all the parallel rays that are coming to the lens will be converged to the focus, or in case it's a different kind of a lens, which is a diverging lens, they would appear to be diverging from the focus behind the lens. So these are some rules that we have developed after studying these mirrors and lenses, and then we can try and develop some equipment to observe these objects in the sky. So yeah, so coming to using these laws and these rules that we have studied, we can easily calculate how we can kind of magnify the image that is in front of us. So you must have looked at sometime, like in your childhood maybe, looked at a spoon and saw yourself like a smaller image of yourself, or sometimes a bigger image of yourself, depending on what angle you're holding it, what distance you're holding it at. So that is because the rays that come the rays that are incident on these lenses or mirrors reflect in certain way. And let us imagine that if we have a spherical mirror here on the right, this is about reflecting, right? So if there is a spherical mirror and there is a, let's say, a pencil that is at this specific position between the center of the spherical mirror that would be and the focus, between that place there is pencil placed, and we can draw a parallel to the radius line going towards the mirror that would obviously go through the focus. And sorry, and then there is another law that if you uh, incident a light ray at the radial line or at the point which is at the center of the entire mirror. So here it's the center of the mirror. So if we kind of extend a incident ray here, so that would be reflected as if it were a plane mirror, because you can imagine a plane mirror behind it and it would act in a similar way. So using these two laws, we know where the light rays would be, and after that we can see that the image that would be formed in a retina or on a screen using these would be larger than the original object itself. So it's magnification in that sense. So magnification factor is basically height of the image versus the height of the object. So in mirrors we can magnify in this way, and in lenses also there is the same law that if you incident a light at the center of the lens, then it would directly pass through as if it were a glass slab. And if it's incident parallelly, then it would travel through the focus. And here again you can see that this pencil has made an image that is larger than the original object. So this is how the lenses and mirrors magnify the original images and how we are able to see the distant objects. So basic layout for a telescope would be that there would be a area where you get your light rays from. Then there would be a filter, and then that filter, after that filter there would be a lens uh, getting it getting the light rays towards a CCD camera. You don't need to understand the CCD now, but let's say you have a camera that captures the photo, so that second lens would be focusing that image on the camera, and you would observe that image. But the lens is not the only way to go for a telescope. There are multiple ways. So there would be a way in which you basically use a spherical mirror, and then there would be an image forming with the magnification. Then there is a Newtonian mirror in which obviously you use again spherical mirror, but you use another mirror so that you can observe the image somewhere else. And then there are some other types of uh, multiple types of formations and combinations that you can use for these kind of telescopes, and you can figure out whatever the best telescope that is for you in general, like whatever your case is, whatever your use case is, and based on that you can figure out what telescope you need. सो अभी तक हमने ये समझा है कि जो हम ऑब्जर्वेशंस करते हैं उसके लिए हमें इंस्ट्रूमेंट्स बनाने पड़ते हैं. तो अलग अलग तरीके के मिरर होते हैं, अलग अलग तरीके के लेंसेज होते हैं. प्लेन मिरर में ऑब्वियस होता है कि एक 90 डिग्री एंगल पे अगर हम लाइन बनाते हैं प्लेन मिरर के साथ, तो जो रे जिस इन वट एवर डायरेक्शन द लाइट इज इंसिडेंट, जिस भी डायरेक्शन से, जिस भी एंगल से लाइट आएगी उसके ऑपोजिट डायरेक्शन में उसी एंगल से रिफ्लेक्ट हो जाएगी। और हम ऐसा मान सकते हैं कि जो ये स्फेरिकल मिरर है जो यहाँ पे हमने बनाने की कोशिश करी है, स्फेरिकल मिरर, वो ऐसे मान सकते हैं कि बहुत सारे छोटे छोटे प्लेन मिरर्स का एक कोलैबोरेशन है, कि बहुत सारे छोटे छोटे प्लेन मिरर्स रख दिए हमने और उसे एक स्फेयर बना दिया, और उसमें फिर उस जगह के हिसाब से हम रूल्स लगाते हैं, और वहीं से सेम ये वाला एंगल ऑफ इंसिडेंट एंड एंगल ऑफ रिफ्लेक्शन वाला रूल लगता है, और उसको ऑब्जर्व करके कि ये कैसे बिहेव कर रहे हैं लेंसेज और मिरर्स दोनों, उनको ऑब्जर्व करके हम कुछ लॉज बना देते हैं। फॉर एग्जांपल कि अगर ये जो सेंट्रल लाइन है जो लेंस के प्लेन ऑफ एक्सिस से जा रही है, सॉरी मिरर के प्लेन ऑफ एक्सिस के पैरेलल जा रही है, वो फोकस पे आएगी, वो फोकस पे इंटरसेक्ट करेगी और फोकस से मतलब फोकस को टच करके ही जाएगी। तो ऐसे ही लेंस में भी होता है कि अगर पैरेलल लाइंस आ रही होती हैं, प्लेन जो प्लेन ऑफ एक्सिस के परपेंडिकुलर है ये लाइन, इमेजिनरी लाइन है ये, तो इससे अगर पैरेलल जा रही है तो वो बेसिकली फोकस से होके जाएगी, और जो भी जितनी भी पैरेलल लाइंस है वो सारी फोकस पे आएंगी। दैट इज व्हाई इट्स नेम फोकस एज वेल। तो उसके बाद क्या होता है कि ये सब यूज करके हम एक तरीके से मैग्नीफाई कर सकते हैं, अपनी इमेज को बड़ा बना सकते हैं। तो मान लीजिए कि आपके पास कोई पेंसिल है और आपने जैसे इस जगह पे रखा है, तो हम देख सकते हैं वो पैरेलल वाला जो हमने लॉ यूज किया था उसको यूज करके हम देखते हैं कि यहाँ पे एक रे जा रही है यहाँ तक, और फिर हम देखते हैं कि मान लीजिए इसके पीछे कोई प्लेन मिरर रखा हो, तो वो तो ये जो सेंट्रल लाइन है, जो जो इमेजिनरी लाइन व्हाइट लाइन बना रखी है, वहां से अगर यहाँ पे प्लेन मिरर लगा दें तो उसकी तरह ही एक्ट करेगा ये स्फेरिकल मिरर भी। तो उसमें ऐसे रिफ्लेक्शन होगा और यहाँ पे हमारी इमेज बन जाएगी इस एरिया में जहाँ पे बड़ी पेंसिल है, इन्वर्टेड बनेगी बट मैग्नीफाई हो जाएगी। सेम तरीके से लेंस में भी यही होगा, यहाँ पे भी मैग्नीफाई हो जाएगी। तो इससे हम इक्विपमेंट्स हमारे बना सकते हैं, टेलीस्कोप्स बना सकते हैं। इनके बहुत अलग अलग अरेंजमेंट्स होते हैं, किसी में स्फेरिकल मिरर यूज होता है, किसी में स्फेरिकल मिरर के साथ प्लेन मिरर यूज होता है, जिससे कि हम कहीं और इस टेलीस्कोप के साइड में अगर हम देखना चाहें तो हम इमेज देख सकते हैं जो हमारा प्राइम फोकस है इमेज का। देन और भी बहुत सारे कॉम्बिनेशंस ऑफ लेंसेज और मिरर्स को यूज करके हम टेलीस्कोप बना सकते हैं। बट उसका इन द एंड यही रह जाता है कि आपका क्या पर्पस है, किस पर्पस से आप यूज करें, एंड आपको कितना बड़ा बनाना है, उसके बेसिस पे आपको ये सब डिसाइड करना पड़ता है आपको कैसा टेलीस्कोप चाहिए। बेसिक लेआउट ऐसा होता है जिसमें कि एक कलेक्शन वाला लेंस होता है जहाँ पे लाइट कलेक्ट होती है, वहां से फिर फिल्टर होता है। तो जैसे कि आप कोई भी चीज को ऑब्जर्व करें उसके लिए हमें बाकी लाइट्स ना आए और कुछ डिस्टरबेंस ना आए, इन सब चीजों के लिए फिल्टर चाहिए होता है। और दूसरा लेंस जो होता है, अगर आपका कैमरा वाला टेलीस्कोप है तो वहां पे कैमरा पे वो इमेज बना देता है। फॉर एग्जाम्पल काफी स्पेस में टेलीस्कोप जाते हैं तो उनमें ऐसा कुछ सेटअप होता है, लेआउट होता है। Then there are different other phenomena that happen, or you can say different difficulties, you might call it. So the telescopes capture image, of course, but you need to mount your lens or your spherical mirror on something. So wherever you mount your mirror on, for example, let's say you have a spherical mirror and you mount it using something like a four-way support. So when you use that four-way support, there is a diffraction of light. So since light behaves like a wave, whenever it passes through something or it has some obstruction, it will diffract. And because there is a support beam on either side in two axes, x-axis and y-axis, there would be a diffraction pattern as such shown in the mounting effect on PSF A part. And if you try and be smart about it and try to say, okay, let's do three spider legs or like support beams, then you will get like six diffraction lines similar to James Webb Space Telescope's lines. Then there are other ways to deal with it so that you get no lines. You can use curved spider legs similar to this one, and in that case you might be able to see a little bit of diffraction, but there is not much of it, and because it is curved. And other way you can use it, you can avoid much of diffraction, is by using a rather circular support for the lens or the mirror. Then this is the result of such a support system, where you use like a 3 spider leg system for support, and then you get this diffraction from the light source. Then coming to other studies that we do after observing, when we record data, then we need to infer what information we have got. And to infer that information, we use something called HR diagram or Hertzsprung-Russell diagram. So this HR diagram is very useful. It tells us a lot about a star, maybe about how massive the star is, maybe about at what age the star is in its life cycle, and we'll study about its life cycle as well very shortly. But it tells us a lot about these kind of properties of star and how massive it might be, how if it is in some special phase of its life, etc. तो जब भी हम कोई टेलीस्कोप यूज करते हैं, उसमें कहीं पे लेंस हमें लगाना है या फिर कुछ हमें स्फेरिकल मिरर लगाना है, तो उस केस में हमें सपोर्ट चाहिए होता है उसको लगाने के लिए, ताकि वो इमेज पीछे तक जा सके। और जब वो हम सपोर्ट लगाते हैं तो उसमें डिफ्रैक्शन होने के चांसेस होते हैं, क्योंकि जो लाइट होती है वो तरंग की तरह काम करती है। तो जब कोई भी सपोर्ट आता है, ऑब्स्ट्रक्शन आता है उसमें, तो ऑब्स्ट्रक्शन से वो डिफ्रैक्ट हो जाती है, यानी कि उससे दूसरी तरफ फैल जाती है थोड़ा। तो जब आप देख सकते हैं ये ए इमेज जो दे रखी है यहाँ पे लेफ्ट साइड पे, तो उसमें 4 सपोर्ट हैं आजू बाजू, और उसके हिसाब से ये लाइट एक्स और वाई एक्सिस में काइंड ऑफ फैल गई है। वैसे ही अगर 3 सपोर्ट आप लगाते हैं तो 6 डायरेक्शन में ये फैल गई है। और ऐसा सेम आप देख सकते हैं जेम्स वेब की इमेज में, जिसमें कि ये स्टार्स हैं। जो ब्लैक डॉट दिख रहा है वो बहुत ब्राइट स्टार है, इसलिए कवर करने के लिए लगा रखा है बस। और ये आप देख सकते हैं डिफ्रैक्शन हो रहा है यहाँ पे। और इसका एक क्रिएटिव आइडिया ये है कि अगर आप चाहें तो एक सर्कल को एज अ सपोर्ट लगा सकते हैं, क्योंकि सर्कल जो है वो कर्व्ड है, डिफ्रैक्शन ढंग से नहीं होगा, तो उसकी वजह से हमें ये लाइंस, डिफ्रैक्शन लाइंस ही देखने मिलेगी। और आप ये भी कर सकते हैं कि अगर आप 3 साइडेड सपोर्ट लगाते हैं तो उसको ही, वो सपोर्ट जो है उसको स्ट्रेट ना रख के उसको कर्व्ड कर दें। उसके बाद हम जब ऑब्जर्वेशंस लेते हैं, ऑब्जर्वेशन रिकॉर्ड करते हैं, तो हमें उसमें उससे हमें क्या समझ आ रहा है वो पता करने की जरूरत होती है। तो उसके लिए हम रिकॉर्ड करते हैं डेटा कि कितना तापमान था स्टार का, या फिर कितना चमक रहा था वो स्टार। तो उसके जरिए उसके जरिए हम एक डायग्राम बनाते हैं जिसको हम बोलते हैं हर्ट्सस्प्रंग रसल डायग्राम। और उस डायग्राम से हम बहुत कुछ पता कर सकते हैं कि उसका वजन कितना था स्टार का, या फिर उसका किस उम्र का स्टार है, कितना बूढ़ा स्टार है, जो कि हम पढ़ेंगे कि अभी ये स्टार की क्या लाइफ साइकिल होती है। तो अपनी लाइफ साइकिल में कहाँ है वो स्टार, हम ये भी पता लगा सकते हैं। सो हाउ वी डू that, how we tell if a star is a small star or a massive star, or if at what stage of its age the star is, we make this diagram in which basically we take surface temperature on x-axis and luminosity compared to the sun. In if you are wondering why this is 1 and 10 and 10 raised to power 2, something like that. So if you're wondering about that, this is because it is luminosity compared to the sun. So that is the unit here, and the surface temperature is in degrees. So here you see that there is a temperature in opposite direction, kind of like in from hot to cold in x-axis, and then less dim, less bright to very bright from bottom to top. And while we plot the data of one specific star on this graph, based on what region the star ends up in, we have already studied a lot of stars, so we know in this region there would be a specific kind of star. For example, in the left bottom left region there would be hot and dim star. Then in the top left region there would be hot and bright star. In top right region there would be cold and bright star, and the bottom right region there would be cold and dim star. So cold and dim star, the dimmest of the star which do not have much temperature as well. So those would be in this region. So you can see the stars here are very red and then turn to yellow, and as we go towards the hot region they turn blue. So basically red stars are uh, less hot and blue star are the hottest. And as we go from bottom to top we can see also the size of the star turns out to be bigger and bigger. So that is also because the brighter the star is the more chances it has that its surface area is greater. It's a more massive star, that is why it's brighter. And you can see sun is somewhere here, and it's obviously one for sun. And in this region these are the average stars. We call these solar mass stars, or stars that are less massive than sun. Then there are super giants in this region. Super giants. On the right side there are red supergiants. These are called red supergiant because they are giant because their atmosphere has swelled up or expanded. And then in this specific region there are white dwarf stars, which are remnants of star. I think someone's asking something. So if you have question, please let me know. Like, just open your mic and ask. So initial of mass of star and what evolutionary stage it is at can be determined using this diagram. Then corresponding to a change in temperature and luminosity, it would be in different region on the HR diagram. So let's say that our star starts off somewhere here in the region below the sun. As the star develops, it burns more and more fuel, and after some while it would reach the region of giants because there would be less fuel. It would start to expand and it would turn into this region of giants. And this would be kind of a track of the life cycle of a star. And at the end it would at the end of the life, star usually blast, and then there are remnants of the star which are sometimes white dwarfs. A star's internal structure
So,
and hello.
so,
Yep.
so you said like फ्यूल कम हो रहा है तो सर फिर उसमें लाइक एक्सटेंड कैसे होगा लाइक वो फ्यूल की वजह से वो इंटैक्ट रखता है फिर ग्रेविटी डोमिनेट कर जाएगी तो मतलब ऑन एन एवरेज स्टार
Yes,
को
yes,
छोटा होना चाहिए लाइक
indeed. But the thing is that the way that this fuel burns is, so the star tries to fuse hydrogen into helium, and after a while when it turns hydrogen into helium there is also hydrogen in its surrounding, right? So it starts to burn hydrogen sometimes in the surrounding region because the reaction that is in the core is not that sufficient. So because there is more and more mass, the star is getting more and more fusion. After a while when at the center there is a lack of this hydrogen fusion, then it starts to fuse helium, and when the reaction outside that core becomes more efficient, then it starts to burn that hydrogen as well. So after some while, due for star to be very stable, what it does is sometimes it expands, and then when the expansion has lost its like, let's say the fuel in the outer region has stopped burning that much. By the way, it's not that far away from the core also. So after that fuel has stopped burning that much, it would start to contract. So star goes like sometimes expands and then sometimes contracts, and that is very short lived period, by the way. Majority of the time the size of star is mostly stable.
ओके
And so The star's internal structure and evolutionary stage or its initial mass simply determines its position in the diagram, and based on where its position is, you can identify like what kind of star it is, whether it is a supergiant or a main sequence. Main sequence basically means the star that is stable and the majority of life how it spends, that is the main sequence. So talking about life cycle of star, so it is a diagram explaining the life cycle of a star. So first there are gas clouds, huge gas clouds. So either there are open clusters or molecular clouds. So molecular clouds just starts to contract on itself because of gravity. Since the gravity is the longest ranging force, and electromagnetic force cancel out in the atom itself. So gravity starts to attract the molecular cloud, and sometimes it kind of breaks into clumps of two or three clouds, or like there could be a number, but let's imagine. So it starts to develop multiple clumps of these clouds, and what happens is at the center of these clumps there would be something like a protostar. So protostar is what's before an actual star is made. So there is a structure, kind of a spherical structure, that starts to form, and it starts to gather more and more mass at its in its body, and we call it a main sequence stars. Once it starts to fuse hydrogen effectively and starts to produce helium, so that's when we call it a main sequence star. So first, from molecular cloud, it makes clumps and develop protostars, and then once the reaction is going and it starts to churn out a lot of energy as the stars do, they would then become the main sequence stars, and for majority of their life they remain the main sequence stars. So based on what mass the star has, it could be a massive star, for example mass greater than 8 solar masses. So compared to our sun, it's 8 times massive. So it would be called a massive star. Then there are low mass stars, which are like in the range of our sun itself, or maybe nearby like 5 solar masses, or nearby like 2 solar masses, or below 1 solar mass. Then there are potential stars that are also called failed stars. These are called brown dwarf stars. You can imagine a brown dwarf as a really big Jupiter. So imagine, so we all know that Jupiter is mostly gaseous. So imagine there was something like a Jupiter, but it was really massive, but not massive enough that it could make the reaction of hydrogen fusion happen. So that is a failed star. So it's already failed and it would remain this way. So its life is like it didn't become a star basically. Then these low mass and massive stars, they continue burning their fuel, and at a certain point when a lot of fuel is burned and they start burning outside and they need more energy, they start to grow in size sometimes, and they become giant stars, or more better call it red giant star or red supergiant star. And in case of a star like our sun, the red giant star, either if it's alone, it would turn into a planetary nebula after an explosion. And what because its fuel is the fuel has run out, and it's after a while it kind of suddenly compacts and there is an explosion, so it turns into a planetary nebula. So in this planetary nebula, at the center there would be a white dwarf star or a black dwarf star. White dwarf star is a very small remnant of the original star. Only let's say only core and some part of the star is remaining. And then black dwarf is when even the white dwarf has kind of died out. And then in other scenario, when there are more than one star in a system, binary star that is called, when it's close to a white dwarf, let's say our sun was accompanied by another star, let's call it sun 2. So sun and sun 2 were revolving around each other, and one of them had already become a white dwarf after red giant, and the other one becomes a red giant now. So there are chances that these stars often interact. So when it becomes a red giant, it kind of grows and it comes into the territory of gravitational well of the white dwarf, and the white dwarf starts eating that star. And after it has increased its mass to more than 1.4 solar masses, that is a very critical limit of the mass. So if it gains mass of 1.4 solar masses, it turns into a super. It bursts into a supernova that is called Type 1a supernova, and then then there are chances for it to become some other kind of object. So it turns into a Type 1a supernova. Then there is another possibility that the mass obtained was less than 1.4 solar mass. Then the blast is smaller and it's called nova, and then it turns into a more massive white dwarf, basically. In case of a massive star which is more massive than 8 solar masses, what happens is a type 2 supernova happens, which is really bright and really big event in which a lot of elements are also produced. Then there is obviously a supernova remnant left because the outer layers would be spread out, so there is a supernova remnant. But there are also two possibilities for its core. Either the core would collapse in obviously the core would collapse because there are no more reactions happening, so nothing is stopping the gravity from collapsing. So either it becomes a neutron star or a black hole. So in case of a neutron star, it remains a neutron star just because the force of gravity is very high, but not high enough to push the neutrons together into a singularity. So we have this neutron star, which is made up of mostly neutron only. And in case the threshold for the density of the core is so high that nothing can escape, then it turns into a black hole. And what you see is the event horizon, and the hole is at the center, which is singularity. Although this is a very simple definition of a black hole, it's not that accurate. Then there are also some possibilities for neutron star and black holes. The possibility for black hole is that there are some debris and there is another star or some other thing that is surrounding the black hole. Then it would turn into a quasar, an active black hole, and it would have some kind of accretion disk around it. Accretion disk is basically matter revolving around a black hole in a rapid way, which starts to emit light. Then the neutron star, the original star, massive star, would also have some rotation, right? So neutron star would also have some rotation, and it might be a pulsar with jets streaming out of its poles from where it's spinning. So these are basically the life cycle of less massive and massive stars and how they end up as white dwarf or black hole. And after that we study the types of stars. So अब तक हमने पढ़ा कि HR डायग्राम से हम क्या क्या पता लगा सकते हैं कि किस एज में वो स्टार है या फिर किस मास का वो स्टार है अप्रोक्सीमेटली, या फिर क्या उसका साइज है। और हम इसकी एवोल्यूशनरी स्टेजेस भी पता लगा सकते हैं कि किस एवोल्यूशनरी स्टेज में ये है। तो क्या वो अभी क्या कहते हैं लाल जाइंट स्टार बन गया है, या फिर अभी वो अपने उस स्टेज में है जिस स्टेज में स्टार्स मेजॉरिटी ऑफ लाइफ के लिए रहते हैं, फॉर एग्जांपल। तो सिर्फ इंटरनल स्ट्रक्चर जो है वो एवोल्यूशनरी स्टेज डिफाइन करता है कि कौन से पोजीशन पे अगर ये है, हम कौन से पोजीशन पे हमने डिटरमाइन कर लिया कि इस पोजीशन पे हमारा डायग्राम में स्टार का डेटा है, टेम्परेचर एंड ल्यूमिनोसिटी, वो अगर है तो हमें उससे पता चल जाएगा कि कहाँ पे कौन से पीढ़ी पे ये स्टार है। और कौन से पीढ़ी का बात करते हुए हम ये पता लगा सकते हैं कि इस काइंड ऑफ डायग्राम से कि जैसे कि पहले एक बहुत बड़ा क्लाउड है जिसमें सिर्फ हाइड्रोजन हीलियम जैसे कुछ एटम्स हैं, और एक बहुत बड़ा क्लाउड है, वो धीरे धीरे क्योंकि बाकी सारी फोर्स न्यूट्रलाइज्ड होती है लार्ज स्केल पे, ग्रेविटी ही डोमिनेट करती है, ग्रेविटी धीरे धीरे उनको पास लाने लगती है और धीरे धीरे वो एक सेंटर पे केंद्रित होने लगते हैं, और केंद्रित होते होते वो एक बॉल फॉर्म करने लगते हैं, गेंद फॉर्म करने लगते हैं। जब वो गेंद हाइड्रोजन के परमाणु को एक साथ लाके फिर हीलियम का परमाणु बना देती है, तब उसका एक रिएक्शन होने लगता है धीरे धीरे, और उसको फिर हम स्टार बोलने लगते हैं। मेन सीक्वेंस स्टार ये नाम दिया गया, मेन सीक्वेंस, क्योंकि मेजॉरिटी जो उसकी लाइफ है, लाइफ साइकिल है, उसमें ये स्टार ऐसा ही रहेगा। और एंड के आसपास आते आते उसमें, क्योंकि फ्यूल की कमी होती है और उसके बाहर रिएक्शन होती है, इन सब कारणों की वजह से वो थोड़ा सा एक्सपैंड करता है और उसको कह देते हैं हम रेड जाइंट या रेड सुपर जाइंट। इस पे डिपेंड करते हुए कि कितना कितना भारी वो ओरिजिनली था। मान लीजिए अगर कि सन के मास के आसपास, हमारे सूरज के मास के आसपास रहेगा तो रेड जाइंट बनेगा, और सूरज से बहुत ज्यादा उसका मास होगा तो वो रेड सुपर जाइंट बन जाएगा। और इस पे डिपेंडिंग करते हुए कि कौन सा जाइंट वो बना है, या तो ब्लास्ट होके एक प्लेनेटरी नेब्यूला बना के उसके अंदर उसका कोर जो है, जो दब गया है, वो बच जाएगा, वो व्हाइट डॉर्फ बनेगा। और व्हाइट डॉर्फ धीरे धीरे फिर ब्लैक डॉर्फ बन जाएगा। या फिर अगर वो उसके साथ में कोई स्टार है और वो व्हाइट डॉर्फ ऑलरेडी बन चुका था, तो वो उसका मास थोड़ा सा खींच सकता है अपनी तरफ, और खींच के या तो अगर बहुत ज्यादा मास हो गया तो वो टाइप 1A सुपरनोवा बन जाएगा, अगर कम हुआ तो एक नोवा बनेगा, नोवा ब्लास्ट होगा और सुपरनोवा भी ब्लास्ट होगा। जब नोवा ब्लास्ट हो जाएगा तो फिर वो वापस व्हाइट डॉर्फ बन जाएगा। और डिपेंडिंग ऑन कितना मास है ये व्हाइट डॉर्फ का, 1.4 सोलर मास से अगर ज्यादा है तो वो सुपरनोवा होगा टाइप 1A। जब रेड जाइंट फटता है हालांकि तब टाइप 2 सुपरनोवा होता है, और उसमें उसका जो एटमॉस्फेयर होता है जो फिका जाता है बाहर की तरफ, वो तो बचता ही है, और साथ में कोई दो में से एक स्ट्रक्चर बनता है। जब 8 सोलर मास से ज्यादा मास होता है उस स्टार का, तो कोई एक बचता है, या तो ब्लैक होल बचता है या न्यूट्रॉन स्टार बचता है। न्यूट्रॉन स्टार तब बचता है जब 40 सोलर मास से कम उसका मास हो, तब ज्यादा संभावना होती है उसकी। तो तब क्या होता है कि वो जो ग्रेविटी है, वो उसका जोर बहुत ज्यादा होता है, और इतना ज्यादा होता है कि जो प्रोटॉन इलेक्ट्रॉन है वो भी सब क्या कहते हैं, स्मुश हो जाते हैं, एक जगह पे केंद्रित हो जाते हैं और वो सारे न्यूट्रॉन्स बन जाते हैं। लेकिन इतना भी नहीं होता कि वो उससे ज्यादा कुछ जोर लगा लगा पाए। तो सिर्फ इसलिए दूर होते हैं क्योंकि न्यूट्रॉन सेम प्लेस ऑक्यूपाई नहीं कर सकते। ये पॉली का प्रिंसिपल था कि सेम प्लेस कोई भी पार्टिकल ऑक्यूपाई नहीं कर सकता। तो वो अगर रोटेट कर रहा है बहुत रैपिडली तो वो एक पल्सर बन जाता है, जिसके एक्सिस से फिर जेट्स निकलते हैं, और उसको हम दूर से कई बार देख पाते हैं और आइडेंटिफाई कर पाते हैं, इसलिए ये पल्सर इसका अलग से नाम दिया है। और अगर उसका मास 40 सोलर मासेस से भी ज्यादा हो तो वो पक्का ब्लैक होल बन जाएगा। और ब्लैक होल में फिर उसके बाहर का जो सर्कल है, जो ब्लैक सर्कल दिखता है, उसका इवेंट होराइजन होता है, और एकदम सेंटर में उसका जो ब्लैक होल का जो होल पार्ट, जो हम सिंगुलैरिटी बोलते हैं, वो होता है। और अगर उसके आसपास कोई मास होगा तो वो उसके चक्कर लगाता रहेगा, और उसमें से भी कुछ लाइट एमिट होगी, और उसकी जो धूल मिट्टी है वो उसके आसपास गर्म इतनी हो जाएगी कि वो लाइट एमिट करने लगेगी। और अब आ जाते हैं टाइप्स ऑफ स्टार पे। So types of star were initially not defined, and the person who did this was Annie Jump Cannon, uh, and she started to catalog the uh, uh, stars on the basis of their temperature and brightness. And with Edward C. Pickering, the creation of this Howard classification was made, and they classify stars based on their temperature and spectral types. So they used to observe what kind of light is coming from the star, and based on that, they used to identify this is this kind of star and this is that kind of star. And this cataloging became the basis for contemporary stellar classification. And as you can see, this is O, B, A, F, G, K, M. This is like the categories that are given. So O stars are the most hottest stars, and this specific kind of spectral type they have. And there are only 5% of all stars that are brighter than or hotter than the sun. So these O, A, B categories, these are only 5% of all the stars. Then there are M category, which are very less bright and kind of red stars and very low brightness. They are 3 out of 4 stars that are in M class. And our sun is in the relatively bright G class relative to M. And a lot of stars are found in this category, but majority of stars are in M category. So these are the classification of star basically. Then another female scientist or female astronomer came, and she gave a groundbreaking for the time theory that stars are composed mostly of hydrogen and helium. So obviously now we know how universe might have started and how very simple atoms only could form in the initial phase of the universe, and then the gas started to clump, and through the process of fusion in stars other elements were made. But people used to think that earlier that the sun is made of same things that the earth is made of, similar things. It's just very big. But then Cecilia Payne came and gave her theory that stars are composed of mostly hydrogen and helium. And then she also gave her proof that the spectral emission of hydrogen and helium completely corresponds to what we observe in the sun or other stars. And she used Saha equations relating the sorry, ionization states to the temperature, and that's how she formed her basis for the theory of why stars are mostly composed of hydrogen and helium. Then there are other type of stars based on how they interact with their surroundings. So for example, there is a binary star in which there are two stars. So there is a star that has already become a compact object, for example a neutron star or black hole, and then there is a normal star that is revolving with it. So the black hole or the neutron star would have an accretion disk of its own material, plus if the normal star expands slightly or is in a region where the gravity can easily attract the material of the star, then you can see in this image or a drawing, the star's material is being accreted by the black hole or the neutron star, and it starts to make its accretion disk. And while this region is getting hot because there is obviously the star's own temperature that is too hot, and then there is accretion disk which is getting hot because of the dust particles or the atoms that are being collided to each other, and this region becomes very hot and the x-rays are emitted from it. So that's why, because the x-rays are emitted, they are called x-ray binaries. Then there are symbiotic stars or donor stars, which is basically one star kind of rejuvenates the other star. So let's say there is a white dwarf star, there is not much left for a white dwarf star to do in its life. But if it's rotating along with a, let's say, main sequence star, like a supergiant star, so white dwarf or the main sequence star would gain some material from the supergiant or cool giant star. So that is how they are kind of symbiotic. So uh, this can even somehow change the fate of the star. Let's say it was not that massive, so we have mass category here. Maybe it was slightly missing the mass from let's say tipping point towards becoming a massive star, in which case it would turn into a neutron star or black hole. So if there is a lot of mass exchange, it could even end up changing the fate of star into a black hole or neutron star, compared to if it were going to be a very massive white dwarf. So that could also affect the evolution of the star. And we will be covering the next advanced astronomy. सो क्या होता है कि काफी बार हमें कैटेगराइज करना पड़ता है चीजों को एस्ट्रोनॉमी में, तो उसके लिए हम ये कैटेगरी यूज करते हैं स्टार्स की, जो कि है OBAFGKM। ऐसी कैटेगरी है, ऐसी कैटेगरीज बनाई हैं जो हम कंटेम्परेरीली यूज करते हैं एस्ट्रोनॉमी में आज भी। तो ये एनी जम्प कैनन नाम की एक एस्ट्रोनॉमर थी, जिन्होंने एडवर्ड सी पिकरिंग के साथ मिलके ये मतलब इनके द्वारा ये फिर हार्वर्ड क्लासिफिकेशन बनाई गई, और ये आज भी हम यूज करते हैं। और ये इसका बेसिस है कि क्या टेम्परेचर है स्टार का और क्या उसका स्पेक्ट्रल टाइप है, किस तरह की रोशनी आ रही है। तो जो मैसिव या फिर जिनका मास ज्यादा होता है और जो सबसे ज्यादा तापमान वाले स्टार्स होते हैं, उनको ओ कैटेगरी में रखा जाता है, और सबसे कम वालों को रखा जाता है एम कैटेगरी में। तो यहाँ पे एक फैक्ट बताया गया है कि सारे स्टार्स में से केवल 5% स्टार ऐसे होते हैं जो हमारे सूरज से ज्यादा ब्राइट होते हैं, बाकी के या तो बराबर होते हैं या फिर मेजोरिटी, जिसका मतलब है कि 3 आउट ऑफ 4, 4 में से हर 3 स्टार जो होता है वो एम कैटेगरी के होते हैं या फिर इसके आसपास के होते हैं। तो काफी छोटे छोटे स्टार होते हैं हमारे यूनिवर्स में मोस्टली, और ब्राइट स्टार बहुत रेयर होते हैं, इसका मतलब ये है बेसिकली। उसके बाद हमें ये नहीं पता था इनिशियली कि स्टार्स किस चीज से बने हुए हैं, तो सिसिलिया पेन एक और एस्ट्रोनॉमर थी जिन्होंने हमें बताया, जिनकी थ्योरी ओरिजिनली इतनी एक्सेप्ट नहीं की गई, बट बाद में हमें कंक्लूड किया कि ये सही बोल रही है कि स्टार जो है मोस्टली हाइड्रोजन और हीलियम से ही बने हुए हैं। बाद में और क्या टाइप ऑफ स्टार हो सकते हैं कि हो सकता है बेस्ड ऑन कि क्या उसके साथ कोई कंपेनियन है, क्या उसके साथ एक और स्टार है, या फिर कुछ चीज है उसके साथ, सेलेस्टियल बॉडी है, उसके बेसिस पे भी स्टार बनते हैं। कि मान लीजिए कोई ब्लैक होल किसी स्टार को एक तरीके से उसका मास ले रहा है अपनी तरफ, खा रहा है उसको, तो एक रीजन होता है स्टार का जो बहुत हॉट हो जाता है और उससे एक्सरेज निकलती हैं। तो अगर ब्लैक होल या न्यूट्रॉन स्टार के साथ कोई नॉर्मल स्टार है जिसमें एक्सरेज एमिट हो रही है तो एक्सरे बाइनरी कहलाता है। दूसरा एक होता है सिम्बियोटिक स्टार, जिसमें कि एक वाइट डवार्फ या मेन सीक्वेंस स्टार होता है, वो किसी फूले हुए स्टार या फिर सुपर जाइंट स्टार या कूल जाइंट स्टार से, बड़े स्टार से अपना अपने आप की तरफ मास इकट्ठा करता है, बेस्ड ऑन कि क्या वो इतना उसके ग्रेविटेशनल पुल के पास है या नहीं। अगर वो पास में होगा तो उसका मास अपनी तरफ खींचेगा, और इससे उसके लाइफ साइकिल में भी चेंज आ सकता है। मान लीजिए कि अगर वो व्हाइट ड्वार्फ बनने वाला था यहाँ पे, तो हो सकता है कि ज्यादा मास खींच के वो क्या पता न्यूट्रॉन स्टार ही बन जाए। अब चलते हैं एडवांस एस्ट्रोनॉमी पे। So in advanced astronomy, we also learn about the other phenomenons and other events that happen in the night sky. So there is a type 1a supernova that we already discussed. But what is type 1a supernova? As we already discussed, there is a limit of mass on white dwarf. And if the white dwarf crosses that limit, which is 1.44 times the mass of the sun, if it crosses that limit, it would burst into a type 1a supernova. Why is this supernova important and why we are discussing about it? Is because it has a specific mass limit, and there is a supernova beyond that specific mass limit. And since we know already the mass limit, we also know that what amount of energy would be emitted, and then it becomes a very standard. So whenever we observe something of this specific range or this specific luminosity that the supernova has gone off, and it is of that specific luminosity or that specific kind, we can already determine the mass of that uh, white dwarf, which is very obvious. But also, if we also see if we identify that there is a type 1a supernova happening somewhere far away, then we can also look at it and see, okay, its apparent brightness is this much, so distance must be this much. So we can kind of measure distances using these standard events. So it's a very standard event because there is a specific mass for it. So we use it as a standard for our distances. So Chandrasekhar gave a limit to mass of white dwarf. So that was maximum mass theoretically possible for a stable white dwarf star. And using Einstein's special theory of relativity and the principles of quantum mechanics, he concluded that it is impossible for a white dwarf star, which is supported solely by degenerate gas of electrons, to be stable if its mass is higher than 1.44 times the mass of sun. So then it would burst into a type 1a supernova. Type 1a supernova is a type of supernova in a binary system where white dwarf and a giant star or even smaller white dwarf can exchange mass, and once the mass of that white dwarf tips over 1.44 times the mass of sun, it bursts into that supernova. Then there are also other tools that help us study astronomy. For example, spectral energy distribution. This is a diagram or a plot that's been made of flux versus the wavelength. So we study wavelength of light that is coming to us, and the amount of that light that is coming to us. So how that is helpful to us? So we can already see here, let's say this is a star that we are observing, and we are observing wavelength in this range is maximum. So we know where what kind of star it is. If it were any, let's say uh, let's say more hot, then the wavelength uh, graph would have shifted to the left. And we see there is a second kind of other plots. Here you can see other plots towards the right, which are not that clear, but also indicate there is something else. So from that, we can see that there is some kind of emission in infrared wavelengths. So that must be because of something surrounding it. So that is basically emission from dust around the star. So there are so much information we can gain from very simple plots. So spectral energy distribution, plot of energy versus frequency or wavelength of the light. So this is used to characterize astronomical sources, and in radio astronomy to show emission from the synchrotron or free emission and other emission mechanism, and in infrared astronomy to classify young stellar objects. So based on where our plot points are and where we observe these points to be, we can easily classify what kind of emission we are observing, and then based on that we can conclude that it must be dust, this must be the actual star, and etc and etc, and what kind of emission we are seeing. Then there is also this thing about how we can detect these just by observation, these stars, these phenomena that happen, how can we detect them? So for example, let's say you want to detect an exoplanet. There is an easy technique. When the exoplanet will transits its star, there would be dip in the brightness, and based on that dip in the brightness we can even calculate the radius of the planet compared to radius of star at least. So we can calculate that, and we can detect that there is an exoplanet, and we can conclude the information about the ratio of the size of the star and planet. Then in case of a binary system, when two stars are revolving around each other, let's say they cover each other's face when they are rotating around each other. In that case, what happens is when there are both of them are separated in this position, they would both be emitting light, and when they cover each other, this star in front of the previous star has covered some of the region that would have otherwise emitted extra light, so there would be a dip. So based on that we can tell that there is a binary star there, this must be the size ratio of the star, and etc. Then there are other ways to observe and to conclude information about these binary systems. So that would be, one would be Doppler effect. Doppler effect is basically change in the wavelength that is coming to us based on if the source of the wave is coming towards us or away from us. Imagine if there is a bike and it's going from right to left, and when it's coming you will hear a higher and higher pitch, a higher and higher frequency, and once it leaves from your left, then you will hear lower and lower frequency of the sound that it was making. So it's similar, but in case of light. So you can see in this gif, you can see as the star is moving, the area where the lines of emission of the star has been marked is shifting from when it's coming towards us, it's shifting towards right, and when it's going away from us, it's shifting to the other direction. So this is kind of a design diagram of an ambulance coming towards one girl and going away from other boy. So the boy would see the bulb redder, the girl would see the light bulb a little bluer. So the wavelength would be क्या कहते हैं, wavelength would seem to be less in case of the object or the bulb is coming towards us. So based on same Doppler effect, when we observe distant galaxies, and when Hubble tried to observe distant galaxies, what he observed was that the farther and farther he looked, the redder and redder the galaxies appeared from what they should have. So he concluded that in every direction this is happening. This means that things are getting away from us. So basically, he concluded that it must mean that the universe is itself expanding. So that gave us the idea of Big Bang, because we thought if it's expanding, then it must have been a smaller size at some point, and that gave us the theory of Big Bang. And also, this just goes to tell you what all you can learn from observation that seem simple at the beginning but have very profound implications. And then there are these last two topics that are about the techniques that are used in observation. So after Doppler, there is interferometry. So interference is basically when two light sources meet each other at a screen, and they either, if they are in sync, they would make a brighter spot. If they're out of sync, they would make a dimmer spot. So as you can see in this laser light, when it passed through a double slit, it makes this kind of a pattern. Oh, sorry, this is a single slit, but if it goes through a double slit, it makes a similar pattern in which there are bright and dim spots. So using this technique, basically, if you use a single dish to collect data for a galaxy, let's say, that would give us a very dull image of the galaxy, very pixelated image. But if we are using two separate antennas to observe the same image, and then we use interference on it, so for sure there would be some gaps in it, because the light would not be sinking at some places. But if the light is wherever the light is sinking, we observe a relatively very clear image. And in case you change the space, the amount of fringes and the spacing between fringes changes. And talking about this interference, that is similar to how we observed our first image of black hole. And it was a collaboration among many countries and many telescopes. And using entire Earth as a telescope, we used data from every telescope and made it kind of interfere. We observed the black hole at the same time, and after calculating that data, we finally got our first image of the black hole. So we use so many telescopes so far away because of one simple reason, that the size of the telescope that was required to observe that black hole very successfully was approximately the size of Earth. So since we could not afford a telescope or even lens or a mirror of the size of Earth, so we collaborated with each other, and we made certain adjustment and use observational techniques to get the blurry but still first picture of the black hole. And then there is another technique in observation that is called observational gravitational lensing. And this is basically what happens when you observe something, and in between you and the observed object, there is something massive. So what happens is, due to gravity distorting the space time itself, the light that was going to travel towards that object, or was about to be blocked by that object, is actually lensed, and its apparent position changes. So we were going to observe it here, but now, because there is a massive object and the light must travel around it and then reach us, we observe that star or that celestial body to be somewhere shifted from its place. Now, how does gravitational lensing help us? You can see this is an image from James Webb Space Telescope, and a lot of the images have these kind of stretched out look, or smudge like look. Here you can see in the top corner, or wherever you look, there is a very stretched out or spiral look. So these are the images of a galaxy that has been lensed because of a material in between, or maybe there is a galaxy, or maybe there is a massive black hole. So because of that, space time curves, and the image that was supposed to come to us from some other point is coming to us from another point. But you can also see there are some replications of that same image, sometimes two replications, sometimes four replications, and thus we get larger amount of images of that, multiple images of that same object, and thus we have more data on that specific object that we want to observe. So this is the end of the webinar. I hope you liked it. I very much urge you to ask questions if you didn't understand something, and I will try my best to answer. And thank you for attending. Uh, Asta and Ritik Pandey have raised hands. So first, I guess Ritik Pandey, what is it that you want to ask?
सर लाइक द वे यू डिस्क्राइब द स्टार, सो बेसिकली मेरा कहना है कि ये जो स्टार्स होते हैं जैसे ओबी को करके ग्रुप है, तो
जी जी।
आई हैव रीड समवेयर की जैसे पॉपुलेशन 1 स्टार होती है, फिर 2 स्टार होती है, फिर 3 स्टार होती है इन सॉर्ट ऑफ स्टार सिस्टम्स में। तो आप थोड़ा एक्सप्लेन करेंगे तो।
Uh, I'm sorry, I didn't understand your question very well. Can you
लाइक
repeat that?
लाइक देयर आर बिग स्टार्स एंड लाइक लोअर मास स्टार, जैसे पॉपुलेशन
Yes,
1 है,
yes,
फिर 2 है,
yes,
फिर
yes.
3 है, एंड डिपेंड्स कि उनका मतलब कौन सा उनका बाइनरी फॉर्मेशन है या अलग अलग फॉर्मेशन है, तो उस पे मतलब
जी
थोड़ा
जी।
कंफ्यूजन।
So basically, what you're telling about population stars or population 1 or 2 or 3, that has a lot to do with the in time in history of universe when these stars were born. So population basically kind of relates to at what era of the universe this star was born, and based on that we categorize it in population 1 or 2 or 3 stars. And if you are asking about other category, let's say binary stars, so one interesting fact is that majority of stars start out as either binary or a group, but then they sometimes end up like uh, rogue stars. Maybe some star gets launched out in the universe, but mostly there are binary stars. So there is also category of 4 stars group and 3 stars group, but mostly there are binary stars. So based on what kind of interaction they have, or let's say in the slide that is already showing, based on the kind of interaction they have, we can also categorize these stars. And also population, like from telling you from what population 1 and population 2 all this means. So population 1 stars kind of refer to the stars that are very rich in metals. So whenever there is a cloud to form a star, right? So molecular cloud, if the molecular cloud has a rich amount of metals in it, a good amount of metals. By the way, metals in astronomical or stellar astronomy basically means any other material than hydrogen and helium. If there is any other material in a good quantity, relatively of course, then it is called population 1 stars because they are formed very relatively recently. And if the star has very low amount of metals, or like only hydrogen and helium for most part, then it would be called a population 3 or 2 stars based on the amount of you can say metals. So population 3 would be the very initial stars that were formed in the universe. I hope that answers your question.
Yes sir, one more question can I ask?
Yes, yes, for sure.
लाइक सर आई हैव सीन कि लाइक एक मिथ है कि सन का कोई सॉलिड सरफेस होता है, लाइक कुछ प्रोग्रेट करते हैं इंटरनेट पे, तो इज इट रियल और सम सॉर्ट ऑफ मिसकंसेप्शन?
I think that would be a misconception because the majority of stuff around the sun is plasma, and on the sun is plasma, so there is nothing solid about it. Uh, there are structures on sun, like there are structures. For example, obviously, when you heat some liquid, let's say, there are convection currents, right? So in sun, similarly, sometimes what happens is there are convection on the surface of sun, and if you look at a very detailed image of the sun, I might try and look it up. You can obviously you can try and look it up. If you look at the very detailed image of the sun, then you will see some kind of grid pattern or something. That's not very exact, but there is grid like structure. So that is because the convection is happening. If the sun were solid, there would be no convection, right? So that is a myth.
Thank you, sir.
uh, there's Astha, you have a question?
Yeah, I don't have a question exactly. I just wanted to say that the concept of diffraction that you covered, especially with the JWST images, it is very important
Yes, indeed.
uh, to be understood. So I'm glad that this concept was covered, that too really well, because even in the textbooks and even in the online resources, it is not covered that well. And we have to take these diffraction spikes into account while we are reducing the images in the research. So yeah, it was really interesting to see that covered. And by the way, yeah, really really great lecture series. Um,
Thank you.
yeah, I would also recommend it to my colleagues. So really wonderful.
Thanks a lot for the praise. Actually, JWST is a very, and even Event Horizon, the program, that is a very recent event. So probably we'll see very soon in books and articles about that, and they would be really included really soon, I hope.
Yeah,
Then
indeed.
thank you. Then there is Param Kasana. I think he's raised hand. Please ask your question.
Yes, sir. I wanted to ask the question that if we consider the universe, I mean the shape of it to be spherical,
Okay.
so the Big Bang might have started at the center, right? So and everything is moving away.
Okay.
So my question was that if we study the like light which is traveling from the center to outward space. So, according to that Doppler effect, the redshift and blue shift. So, if we analyze and can we find like where the Big Bang took place?
So
It won't be possible to reach there and all, but would it be possible to deduce where on which place it all started? Because we can also think like as everything is expanding and moving away from each other, so it might create a empty space there. I guess. That's what I was thinking.
so the thing is that this is quite complicated, how everything is expanding and the universe itself is accelerating even while expanding, and how this is happening, it's quite complicated. So what we talk about basically is our observable universe. We are pretty sure that there is something beyond our observable universe, but we are not sure if it's infinite or how big it is, right? So we talk about observable universe, and we say that whatever we can observe and whatever that has that includes us, has started this 13.8 billion years ago or something, and we talk only about that. And when we talk about that, then there was no space to begin with, right? There was no space to begin with, and even the space started at that point. So if we consider that singularity or whatever, if the space started at that point, then it becomes clear to us that the expansion is literally everywhere, and like it's there is no center to it, because everything you can, maybe you can understand it in this way, that everything was at center only, so there is no center to the expansion. And when it's expanding, the probable future for the universe is that everything will expand and go away, and like everything will be cold and there would be no life or something like that. But that's very distant. But the probable explanation for the end of the universe is that everything would go away and there would be nothing left in like for distances that are unimaginable. There would be nothing to see. So yes, that would be kind of a vacuum, but we really don't know what would happen then.
Oh, okay. Thank you. Thank you.
You're welcome. So if anyone has any other questions, please ask. And also, I am reminded of something that Param just asked. So he was asking about if we can observe the older or the Big Bang or something. So the image that you see just here. So in this image, it shows what is the limit for Hubble Space Telescope and James Webb Telescope. So what happens is the farther we look, because the universe is expanding, right? So the light takes time to travel, and if something is, let's say, 10 light years away, then it means the light has taken 10 years to travel to us. If we are observing something like 3 billion light years away, then it has taken light 3 billion years to come to us. That means that we can basically look into the past of the universe, how universe used to look like. So there is a limit to Hubble's visible range, because it observes in visible range. So there is a limit, since since because of the expansion of the universe, the light is stretched out and more red compared to the visible range. So that makes it easier for Webb to observe that red region. And since it deals in infrared region, the the James Webb Space Telescope, it deals in infrared region, so it can see even farther objects. So because it sees infrared rays, the stretched out light rays, then it can see even farther images. It can take even farther images, and it can look into the very young universe. And still there are like possibilities and for gravitational wave kind of telescope to be formed, but that's far fetched for now. But that's how far we can see. So it's kind of a present day and the start of the universe, kind of an arrow here. And then you can see the range for which the how far into the past our telescopes can see. If everyone's questions are answered.
Sir, one more
Okay.
question, quick question.
Yeah, sure.
Yeah, so as you said, we are expanding, right? So there must be some galaxies or like some structures which will move towards us. Like some things will go farther away from us, and some will move towards us, relatively comparing. So,
uh, so that would not be the case, because
okay,
everything is expanding. So the space itself is expanding, right? So it's expanding everywhere equally. It's only when we talk about very huge scales that we see that okay, the universe is expanding at the speed of light. But that's only when we compare edge to edge. But in the inside, everything everywhere is every space, I mean, everywhere is expanding. The space time is expanding. So the galaxies that are close by would be held by gravity, but the galaxies that are distant would only drift apart. It's okay. So one thing that you can really understand this by is, if you have a, let's say, a balloon, you draw some dots on it, on the balloon, which are equal distant. When you blow up the balloon, every dot would have moved away from each other, no matter where you placed it. So no dot would go towards the other dot. Every dot would be going away from each other. So that way, maybe you can understand how the universe is expanding.
oh yeah, yeah, yeah. So okay, 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 okay. So you mean to say that space is not expanding in a particular way, like
No, no particular
uh,
direction. Yes, there is no direction.
okay, it's
Yes,
expanding everywhere. Okay, oh, oh, cool.
you're
Thank you.
welcome. I think Nadi, or I'm sorry if I'm pronouncing the name wrong, has a question. Is it possible to see the light from earlier or before Big Bang? There is a star that has been detected by telescope that has age older than Big Bang. Okay, so the thing is that obviously you cannot see before Big Bang. The reason why I say that is because we can already not see anything that is beyond the cosmic microwave background. So if you remember, we saw this image, uh, the image in the bottom right corner here. So this image specifically is of microwave emission from the time when light was allowed to escape from the clouds. So that's a discussion for some other time. But imagine that there was a light suddenly in the universe. The light was always there, but it started to easily escape. So this is an image of the stretched out light from that period of time. So this is a microwave image, not even infrared. So beyond that, we do not have telescopes yet. So we do not have telescopes to see beyond microwave or something. So we cannot have a star that is older than the age of Big Bang. Obviously, there could be some kind of error in what was measured. Like maybe the age was measured with some error in it, or maybe there was some error in the calculation or something. But mostly the case is that the stars are born way earlier in the universe than we expected, and people in the news kind of mix it up like the star is older than the Big Bang itself or something. Sanya has asked if universe is cyclical with repeating Big Bangs. So there is a kind of a theory. We do not have a way to test it, but there is a very plausible theory that maybe the universe can, like, if let's say our universe was doomed to collapse, then it would have been very plausible theory. But right now there is no way to prove it. So there is a theory that a universe comes into existence with a Big Bang and then goes out and then comes into existence. But yeah, it's just speculation at this point. It's not a very solid theory or scientific theory. uh, I think I've answered questions in the messages as well. The tired light theory. I do not understand what the tired light theory is. I don't know of this terminology, so I cannot explain it. But by that, maybe by reading that, I simply think of redshift, but I'm not sure what tired light theory is. Sorry. I think the questions have been answered. If anyone has any question, please raise hand. Okay, so I think it's been answered. So I guess that is it for this webinar. I hope you all learned something interesting and you learned something that was very basic and understood how our ancestors did the science and how today we are doing this observational astronomy. And thank you all for attending.
Thank you, sir.